Right, excellent. As the introduction mentioned, I run and co-founded a company called Geoptic. We specialize in the measurement of natural background radiation for many, many down-to-earth and mostly engineering applications. Um, and so more recently, we've been studying, in part because two of the co-founders of the company actually proposed it in 2010. And so we've been studying the use of cosmic ray muons. And I'll go into what I mean by that very shortly. I'm also speaking some of the work, a lot of the work that's presented here is as part of a number of partnerships that we've had. And so I'll talk at the end about some of the results that we've had from the Svelvik test site, where we partnered with Syntef on. So just to start off, I'd like to talk about perhaps a more familiar example to everybody, and that's really X-ray imaging. So in the medical X-ray imaging case, you have a source of man-made source of X-rays. Those are emitting X-rays through maybe a hand, or if you're in the engineering community, an object, for instance. And what I really wanted to get across here is that that picture that you see on the right-hand side, yes, it is, a very helpful picture. But also, if you were to think about the areas which are black on that picture, those are the areas where you get the full beam of particles, of X-ray particles. And where you get the denser regions of the hand, you have the white areas of the hand there. Fewer of those X-ray particles are actually making it through the hand to the detector. And so by counting particles, it can give us some material discrimination. And that's the same principle that we apply to muon imaging. And so the other more technical point I should make on that is because it is a particle counting measurement, we understand and we know the fluctuations on those quite readily. So as part of our work to a number of our engineering customers, we provide a measure of confidence in our results as well. So this is the space bit, and this is actually the source of our radiation. And it's a natural process that goes on in the upper atmosphere, approximately 30 to 35 kilometers in the upper atmosphere. So the Earth is bombarded by protons and other ions, and those collide and crash into a lot of the atmospheric molecules, causing a downward shower of many other types of particles. Because all of these particles come from outer space or have that connotation, they're often termed cosmic rays. And so we deal with one particular part of this rich spectrum of particles called muons that dominate at the surface of the Earth. These come down and they're passing through you right now. So the popular science bit is if you hold out your hand, you'll have about one through your hand per minute. And so we use this flux and we measure the rate of cosmic rays passing through man-made structures, the subsurface, in order to then infer density. And that's primarily the technique. So there's a couple of properties of our source that it's the one thing that we can't change about the technique. So we have to be very mindful and to either design our study accordingly. And so the one on the left is actually both showing the high penetrating power of the particles. I mean, people have measured them down to 15 kilometers of water equivalent. However, that's at those sorts of depths, it's not very useful because the flux is so suppressed that you'd be waiting a long time to get sufficient particles to be able to discriminate between materials. So for this technique, we're very much concentrating on depths that are less than around 3 kilometers of water equivalent. So these are your shallow CCS sites. The other property of the source that we need to be very mindful of is actually that most of the particles are coming down from the near vertical or within a 60-degree cone of that. And as you start to point your muon detector closer to the horizon, those particles fall off approximately as the cos squared, which is to do with the path length in the atmosphere. So more of the lower energy muons get attenuated by the atmosphere. So the rate of muons is actually also at the surface of the Earth is also lower. So this has really seen quite an explosion of interest in many different applied areas of science. And so it's certainly in the UK, it made the national news about the discovery of a new chamber in the pyramid of Khufu by the same technique by Japanese and French groups. There's volcanology experiments. We do a lot of railway tunnel imaging in the UK, supporting the National Railway operator to identify any voids or shafts above tunnels. And there's been also work looking at water ingress, looking at density changes due to that. And then lastly, we've also recently completed a project with the US DoD looking at transferring position information, GPS information, underground and underwater as well. So the picture on the right is actually from Lake Kilpisjärvi in Finland. This is the principle really for CCS. As you are probably aware, we're talking here about when you're injecting with CO2 and you're causing a density change within the subsurface. Gas into gas is probably not the right sort of study for this technique. And so in this case, we would imagine it as a downhole instrument that then has a number of lines of sight going up through the subsurface. And along those lines of sight, we've isolated the part of the muon spectrum that's coming down from the upper atmosphere. And so we're measuring any changes in the muon rate along those lines of sight, and those changes can be correlated with density along those lines of sight. And so again, just to exploit the analogy of the medical x-rays, again, if you have multiple views of the subsurface, you can then start to move to tomographic reconstruction as well. And so in the experiment that I'll be talking about in a second, we actually deployed a chain of around 13 detectors into the subsurface. So why might this be interesting? We heard earlier from the current state that there's competition or coexistence that's needed between CCS sites and wind turbines, especially in the UK part of the North Sea. The technique actually has a strong directional sensitivity. So there's been work, for instance, from a Los Alamos group, which actually exploited this and used muons and gravity to better define a long elongated structure in the subsurface above one of Los Alamos's tunnels. And in that case, then it's actually a publication by, I point you to was a publication by Gardi-Cherry, Elena Gardi-Cherry on that. On the seismic side of things, this technique really is a secondary density measurement technique. So it's there in that supporting role to seismic, where seismic makes assumptions potentially about velocity density relationships. Muon measurements could be there to support and improve the precision of those measurements. So there's been prior work within the community looking at joint inversion, looking at also feeding in, for instance, the low spatial frequency reconstruction for muons as a prior guess for seismic reconstruction as well. So just to provide on the flip side a little bit about the expectations that one should have around this technique. And so our challenges really are around that flux. Again, I said it's one thing that we can't change. And so our previous simulations, so this is in the North Sea. So there's a study that's published by an author called Klinger. We've also simulated the Sleipner site and more recently the Svelvik test site. And actually for that last simulation, that was actually taking data from an eclipse model of the subsurface as well. So we take that data and then we take it into our own computational software, which is based upon CERN's Jan4, which governs all of the interactions of muons with different materials. And so from our very brief numbers of studies, we're starting now to sort of try to bound the region of interest. There's a couple of reasons why I would say that probably the very shallowest of sites are of the most interest for this technique. One is that as you go deeper, you get fewer muons, and so that time increases. And here, for most of these sites, we're talking about an integration time of the order of 2 to 3 months. It really is dependent upon the site, however, and the depth primarily. We've also performed some instrument testing as well to qualify our detectors down to this depth as well and temperatures. I don't really have time to go into the simulations, but because I kind of wanted to show you what we were up to last year. And so we were at the Svelvik site. So in summer of the last year, we built a batch of muon borehole detectors. It was a batch of 30, and that was primarily because for this project, we wanted to, of course, demonstrate sensitivity to CO2 in the subsurface. It's a very shallow CO2. It was the same site that Michael mentioned. But we also wanted to demonstrate that deployment of a significant number of muon detectors along the way. So we put muon detectors around M3 where we expect the plume to arrive. And then there was also a significant program of seismic work, some of the data which Michael showed earlier. This is a schematic of our detector. It's approximately 60 millimeters wide. That's also because we're co-developing for some of the mining sector as well. And then we have a sort of deployment. We actually hung the detector string off a drill rods actually, but we've later designed it actually for a steel cable deployment. And so then some of the seismic data, again, some of this was also shown in Michael's talk. The net output of this is that we saw the plume, there was around 3 tons of CO2 injected over 30 days, and we saw the plume arrive approximately 3 days after injection, and then leave approximately the same after the injection was stopped. And one of the results is shown on the right-hand side, which is the reconstruction of the density from the seismic data only, showing a plume that's approximately 5 meters away from that M3 borehole where we placed our muon detectors. And that was particularly interesting because independently, we also reconstructed the muon data. And so what you see on the left-hand one is, which is our a 3D representation of the data, is that you see this sort of ice cream cone type of structure, and primarily that's associated with the lines of sight going up and giving a vertical blurring associated with the data. However, when you start to look at the width of this plume, and this is the change in density from our baseline model, I should add, you start to see widths that are comparable to the seismic data. And so that was a very quick canter through muon imaging, applied to CCS, and then hopefully try to make touch points about things like the multiphysics nature that you have here. Sorry.
Thank you very Ooh.
Okay.
Thank you very much, Chris. I would invite everyone to join, all of the speakers to join
Okay.
the panel. So please find the seat as well. Can I ask everybody to please raise the hands again? Because, oh